So what we were talking about last time is the stress response, yes? The endocrine stress response. Does anybody remember the name of the process? It's a 3-tiered stress response, and the name of it doesn't sound like it has anything to do with it. Do you remember what it's called? Nobody does, because somebody named it poorly. But I didn't get to name it, so don't hold me responsible. What's it called? General adaptation syndrome or general adaptation response. I have no idea why the hell it's called that. Like, why didn't they just call it the endocrine stress response, right? That would be better. But it's called the general adaptation syndrome or the general adaptation response. So let's go back to what we did last time, and then we're going to add more to it. You ready? So we are talking about the endocrine stress response. Of course, guys, we are going to talk about the nervous system stress response when we get to neurotransmitters. Why is the endocrine stress response so important to understand? Well, because it doesn't stay localized to the nervous system, right? If you dump hormones into the bloodstream, you can end up having an impact on a whole bunch of different body systems. So the endocrine stress response ends up being pretty important. It's also going to be something that I would be willing to bet that every single one of you will have some experience with, because I'm pretty sure that most of us do not live lives with 0 level of stress with an entire suite of people that are just catering to us at every moment. So the first tier of the stress response is the alarm phase, the acute stress response. The hormones that are involved are primarily what? What hormones? Epinephrine, a little bit of norepi, and a little bit of dopamine. That's primarily what you have, right? And we deal with that, of course, every time that we get excited, every time that we get stressed out or scared. That's the epi-stress response. It becomes hormonal, remember, when you dump it into the bloodstream. And then it can have broader effects than just cardiac muscle, smooth muscle, and glands when it's released hormonally. Who can remind me what are the effects of hormonal epinephrine? Hormonal. What does epi do when it's released hormonally that it doesn't do when it's just released as a neurotransmitter? You can look if you need to. I'll wait. Yeah, and what it can. No, heart rate already happens. Yeah, it's the metabolic effects, right? Yes, the metabolic effects, right? It does gluconeogenesis, yeah, if necessary. Glycogenolysis, right? Dumps it into the bloodstream, right? It can also increase skeletal muscle metabolism and skeletal muscle activity. So it can only do those things when it gets dumped as a hormone, because if it was released as a neurotransmitter, it wouldn't get to those targets. Everybody okay with that? Remember, that's what we talked about last time. That's why when a type 1 diabetic kid goes out to recess, he needs to calculate that in to what he's doing, because he's going to get epi released as he's running around on the playground, right? Does that make sense? And it's going to up his blood sugar. Okay. So that is the alarm phase. And we said the alarm phase is not necessarily a negative thing, but repeated activation of it can increase your blood pressure and deplete your resources. Yes? Okay. All right. So now we're going to get to the interesting part to me. The next phase is the resistance phase. And the resistance phase primarily involves 2 other hormones. The resistance phase is really this part, when we are primarily going to cause the release of cortisol and corticosterone. And whenever you release corticosterone, it causes you to release, what's the hormone? Aldosterone. Okay. So the primary thing that you have with this chronic stress, called the resistance phase, is you have the release of slightly more cortisol and slightly more aldosterone, but really continuously. Does that make sense to you guys? Okay. And so here's what happens, guys. Due to chronic stress, yes, what you are going to do is release different hormones. And chronic stress, let's broaden our definition of chronic stress to say that if you had a chronic disease, that would be a chronic stress. If you had an injury, that would be a chronic stress. If you lived in a household in which you were about to get the lights turned off all the damn time, that would be a chronic stress. If you lived in a war-torn area, that would be a chronic stress. If you lived in an abusive situation, that would be a chronic stress. Does that make sense? All of these are potential chronic stresses, as are the classic ones like starvation and disease and those kinds of things. So what's going to happen in this situation is this more chronic lower level stress is going to cause the release of CRH from the hypothalamus. You with me? yes? And then cause the release of ACTH, okay? And then the adrenal cortex will respond by secreting cortisol. So what we really need to understand now is the impacts of chronic cortisol secretion. Now, this is totally fine when it happens every day to keep you alive when you're asleep, but when you're doing it really chronically, it's going to end up depleting a lot of your resources and depressing a lot of your body system. So let's look at what happens. So cortisol is basically a friend when you are in need, but if it overstays its welcome, it's going to jack everything up. So cortisol's objective is survival until things get better, but it's never sure that things are going to get better. So what it does is says, I want us to not spend any attention, any energy, any blood flow on anything that won't get me through the night, right? But the night never ends in this chronic cortisol secretion. So it's a friend when you're in need, during sleep, chronic illness, or starvation. But when it overstays its welcome, it's going to cause serious depletion and damage. And let's see the kind of damage it can cause. Okay, most of the cortisol effects are metabolic. It mobilizes fuel, glucose, amino acids, all of that stuff into the bloodstream. But if you do this continuously, guys, if you do lipolysis continually, if you continually break down your proteins, decrease protein synthesis, do gluconeogenesis, what's going to happen is you are going to lead to a gradual depletion of your stored resources. Does that make sense? You're just going to kind of use them all up all the time. And then are you going to build muscle mass under a situation like this? No, not very readily. It's very difficult to build muscle mass because you are constantly, whenever your sugar is low, you're going to immediately do glycogenolysis and gluconeogenesis, okay? Now, what is going to be the effect on your metabolism if you depress your muscle mass, decrease your muscle mass? It's going to decrease your metabolism, so keep that in mind. In addition, gluconeogenesis is, of course, going to begin in the liver, and you are going to start tearing down your body proteins, muscle first and then bone, and you're going to convert them to glucose for energy. So you are literally tearing your structure of your body apart due to chronic cortisol secretion. Does that make sense? Okay. Now, non-essential tissues, anything that wouldn't get you through the night, but the night never ends, are going to be, for instance, all of these tissues up here. These many tissues, you decrease glucose uptake, you decrease amino acid uptake, you basically tell those tissues to suck it because we don't need you right now. Now, that ends up being problematic when you do it over long periods of time. It will decrease growth, it will decrease repair, it will decrease reproduction, and it will depress your immune system because the immune system is really preparation for the future, isn't it? But if you're not sure the future is going to come, then you end up depressing your immune system, especially the smart part of your immune system like T cell production. Okay, does that make sense? So how does this manifest in people? What you will get, these non-essential tissues in people who have chronic stress is, as far as fertility goes, you will have decreased fertility, more trouble getting pregnant. You will have miscarriages during the first trimester, more common with high cortisol levels. And men, it manifests as erectile dysfunction. Now, is this a dependable birth control mechanism? No, otherwise poor people and starvation conditions would never get pregnant. But per individual, have you ever known anyone who a couple is trying to get pregnant and trying to get pregnant and trying to get pregnant, and they just can't get pregnant, and then they completely give up? Or they adopt. And then what happens? They get pregnant because cortisol secretion will cause erectile dysfunction, decrease fertility in both sexes, and also increases the likelihood of miscarriages. So if you can get your cortisol to let off sometimes that can help with fertility issues. Okay, so the net reduction in metabolism of all of these non-essential tissues and also the net reduction in metabolism from losing muscle mass is this. Weight gain whenever nutrients are adequate. So in the United States, most of us, even when we're stressed out, do have adequate access to nutrients. They may not be quality nutrients, yes, But even, for instance, in inner city, very poverty-stricken areas, you have access to a decent amount of nutrients. They may just be really low-quality nutrients. High sodium, high fat, high sugar, very low nutrients. So what happens if you depress your metabolism and then feed yourself adequately? Yeah, you store it. You get fat. Yes? So, and you get fat in a way that cortisol makes you get fat. Where does cortisol make you get fat? Like with Cushing's. Right around the middle, which is the worst place to get fat, yes? Now, in other situations, if you depress your metabolism and you don't eat or you can't eat, like starvation conditions or sickness and those kinds of things, then you're going to lose weight, right? But if you have that combo that we have in most places in America of nutrients plus low metabolism, then you're going to gain weight. Now, the other thing is that, what do you think that dumping all of this sugar into your bloodstream chronically is going to increase the likelihood of type 2 diabetes? Okay, so I want you to think about the poverty-stricken portions of America right now, and you can see that what is typically true is that you have obesity associated with it and an increased likelihood of type 2 diabetes. And then we've also got some other things. The other impacts of chronic cortisol secretion are immune system. So the immune system is one of the many tissues that gets depressed. The immune system gets depressed, especially long-term immunity like T cell production and antibody production, because you don't trust that tomorrow is coming. So cortisol is an anti-inflammatory, but then you are decreasing inflammation and decreasing T cell production chronically. It also means that you probably won't heal as readily because inflammation is the first step of healing. So you reduce antibodies and reduce T cells. Now this is a big deal because it lowers your resistance to every disease you get exposed to. It also lowers your resistance to cancer. I don't know if you guys know this, but there are T cells that are called natural killer cells that actually gobble up your own precancerous cells, and you have just depressed the production of those chronically. Okay, so the vessel impact also exists. So remember that I told you that cortisol is supposed to make your vessels respond when you tell them to, but now I'm secreting cortisol all the time, so your vessels are always slightly constricted. What does that do to your blood pressure? Yeah, it raises your blood pressure. Okay, all right, so here's the new research. This isn't in your textbook. It only came out about 3 years ago, and it usually is an 8 to 10 year cycle before something that comes out and it makes it up into your textbook. Some of this research was done by Sapolsky, the guy that I introduced you guys to, that works at Stanford. He's a primatologist. He studied this first in baboons and then confirmed it in humans. It's pretty damn interesting. And now that I see it, it makes total sense to me. So there are brain impacts of cortisol, chronic cortisol secretion. And they are basically that there are portions of your brain that are necessary to get you through high stress or vigilant situations. And there are portions of your brain that are used for the future. The impact of chronic cortisol secretion is that it tends to increase blood flow and even mass of the portions of your brain that are on heightened alert because you are stressed out, including the amygdala. So increased blood flow, increased mass of the amygdala. That manifests as anxiety, sort of reactiveness, and also sleep disturbances. Does that make sense to you guys? And why? Because you're chronically secreting a hormone that says, we might be under threat, we might be under threat, we might be under threat, right? But then the effect of chronic cortisol secretion on other portions of your brain, the portions of your brain that do complex intellectual processing, that do delayed gratification, self-discipline, planning, decision-making for the future, even if it's a decision that is not going to benefit you now, those things happen primarily in the prefrontal cortex. Cortisol decreases blood flow and decreases the thickness of the prefrontal cortex when secreted chronically. Isn't that interesting? So what happens is chronic cortisol secretion will make your brain react and develop differently. And I want you guys to think about how that would impact a child growing up in a situation in which there is chronic cortisol secretion, a child growing up with starvation or violence, or those kinds of things in their household. So it decreases prefrontal cortex activity, and your prefrontal cortex allows you to put off the thing you want now for the thing that you want far more in the future. right? And that's difficult for all of us at the best of times, isn't it? Right? Especially before age 25. Okay, other things, and then we'll come back to that. Okay, so the other things are, you guys have known for ages and ages that associated with stress tends to be ulcers. And we used to think that if you've got ulcers, just stop being stressed out and you won't get ulcers. But now we realize that the connection is probably that when you depress your immune system, you allow for a bloom of a bacterium that exists in most of our guts called Heliobacter pylori. We keep it down, we keep our foot on it most of the time with a healthy immune system. But when cortisol is secreted, over-secreted, it depresses your immune system and you get a bloom of Heliobacter pylori, which destroys the lining of your intestines and your stomach. And also probably reduce blood flow to the GI tract. This one's kind of interesting because what happened with this is that there was a research doctor, who was pretty damn sure that ulcers were caused by bacteria, but no one would believe him, and he couldn't really get permission to experiment on a population in which, for instance, I dose you with Heliobacter pylori and you get an ulcer, and then I treat you with an antibiotic because it's a bacterium, right? So he did it to himself. He dosed himself with Heliobacter pylori, got an ulcer, treated himself with the proper antibiotic, and it went away. And that's how we started changing the way that we actually treat ulcers. So they're primarily related to bacteria and because of depressed immune system. Okay, so we are also going to have, as Anna said, aldosterone secretion whenever we have glucocorticoid secretion, right? So what are the long-term impacts of chronic aldosterone secretion, guys? Do you remember our friend aldosterone? This is what it does, right? Aldosterone causes you to retain sodium at the expense of potassium. So the net effects of oversecretion of aldosterone are that you retain sodium and water in the body, yes? What does that do to your blood pressure? Raises it. And you also can potentially excrete too much potassium into the urine, which leads to which kalemia? Hypo. And hypokalemia causes cardiac arrhythmias. Remember that. It doesn't necessarily cause a heart attack, but it increases the likelihood. Good? Okay. So here is the net hormonal effect of chronic stress. Chronic. What is chronic, by the way? How many months? How many years? It's different for different people. Probably 4 months in physiology is not going to cause you chronic stress. But maybe. So the net hormonal result of chronic stress is that you have an anxious, sleepless person, right? Because of two things. First, you continue to release epi relatively regularly. And then second, you've increased the activity of the amygdala. High blood pressure for 2 reasons, yeah? Relatively few energy reserves. So if something really bad and they actually get ill, they're going to have a hard time getting over it. Higher probability of cancer, higher probability of ulcers, catches every damn weird-ass germ that comes around. Like bird flu, you're going to get the bird flu if you're the person who's stressed out. And you've been in that situation before, haven't you? Right? The more stressed you are, the less time you have to get sick. What's going to happen? You're definitely going to get sick. That's what's going to happen. So catches every germ that comes around. You have a higher risk of a myocardial infarction. You have a higher risk of type 2 diabetes. And this is really important. You also have decreased coping skills. You have decreased processing. You have decreased decision-making skills. You make the worst decisions in your life when you are stressed out because of increased amygdala activity and decreased prefrontal cortex activity. So here's my question to you guys. How do you think that all of this is going to differentially affect a child who is growing up in a violent situation with potential disease and potential poverty versus my kid? Both kids may have started out with the same predisposition to the same level of intelligence. What do you expect about how frequently kid A is going to miss school, for instance? He's going to miss more school, right? And that correlates, by the way, to academic performance, especially with children. There's a certain little cutoff at which it correlates. How do you think he is going to be likely to engage in the planning that will get him the success that he needs in school? No, he's probably not going to. How about his behavior in school? more likely to have behavior problems, right? All of those things. And then more likely to have failure to grow as well, right? You can actually have decreased growth as well because growth and reproduction is inhibited. And his immune system is poorer, and his behavior is poorer, and his prefrontal. Ask him to do a calculus problem, right? Versus asking my kid to do a calculus problem. They're both going to get stressed out because let's acknowledge that calculus is stressful, right? But which one is going to have the coping skills to deal with it? Probably the kid who doesn't have chronic cortisol secretion. So this is kind of an interesting thing because what we tend to do in this society is assume that everyone who is given the same opportunities, right? Same school, same teachers, same opportunities, is going to have an expectation of the same outcome when their opportunities were actually changed long before that, right? And it's at least worth acknowledging. Okay. All right, so the next stage. There are two possibilities at the next stage. So now we have done this for a really long time. So there's a couple possibilities. The stress can go away, right? You could have been on the verge of poverty and about to lose your home, and then you got a good job and everything settled out, right? And you're like, okay, I got through that. Or you could have had a chronic disease like cancer and you're actually in remission for cancer. And then what's going to happen in that situation is this actually did work. It kept you alive until stuff got better, right? It may have done some damage in the process. It may have been costly, but you know that sometimes you have to use up all your crap to get through a bad time, right? And this is one of those times. So if you can either get rid of the stress, right? Or sometimes if you can recategorize it so it doesn't seem stressful to you, right? Like therapy. You get in a situation in which like the same experience can cause a different response in you because you've changed your perspective on the experience. Regardless, if that occurred, then what is going to occur is you get through the stage of recovery. And all of those mechanisms were fine, although costly, to get you through this. The high glucose, the fat, the amino acids in the bloodstream, even the depression of the metabolism was useful. And then you get homeostasis restored and you get regeneration of your cells and it was successful, right? So it kept you alive. That's fine. Okay. So the negative feedback was fine. The stress stopped. The negative feedback says, okay, we don't actually have to secrete anymore, CRH, ACTH, all that kind of stuff. But what if the stress doesn't go away or you don't figure out a mechanism to make it not stressful to you? And that is how a lot of us live a decent chunk of our adult lives, okay? And we need to consider the physiological impact. The physiological impact, if you don't get rid of or recategorize the stress, is that you're going to get all of the things that we talked about. And stressed out people tend to die from a certain collection of diseases. And so if the stressor is not overcome, you lose your negative feedback inhibition. And why do you lose it? Because this is trying to inhibit, but you continue to put in the stress. It's trying to inhibit, but you continue to put in the stress. Just like the situation with type 2 diabetes. I'm trying to take care of this, but you freaking keep drinking Dr. Pepper. Same thing, right? So you continue to put in the stress. So if the stressor's not overcome, your negative feedback loop does not work. So death can occur and does occur in people who are really stressed due to opportunistic infections, meaning that my kid probably wouldn't get bird flu when exposed to it, but the other kid would. Yes? Okay, opportunistic infections, complications due to diabetes, cancer, shock I'll talk about in just a second. Depletion of potassium, hypokalemia can lead to cardiac arrhythmias, increased myocardial infarction. If you do this for a long time, you'll also probably have all of the complications of obesity here in the United States, right? Let's talk about shock. So remember that we need cortisol in order for our vessels to respond, right? But if we're chronically secreting cortisol and I get into a car accident, here's what happens to most people when they get into a car accident. Your blood vessels go massive vasodilation, but then you vasoconstrict, right? But if I get into a car accident and I'm super stressed out, you go massive vasodilation. I don't have any cortisol. I can't respond to the command to vasoconstriction. So what happens is I die of shock, right? My blood pressure drops so much and I can't contradict it. And that doesn't happen to a person who doesn't have that particular lifestyle. Does that make sense? Okay, so all bad news. What's the good news? There is some There's a little good news. You ready? What the hell can you do? Well, don't yell at yourself and say, stop being stressed out, because it doesn't work, right? Does it ever work when you yell at people and tell them to calm down? That parenting technique has failed over and over again. Calm down! Okay, so what can help? Reduce your cortisol levels, easier said than done. The usual suspects for reducing your cortisol levels are stop being stressed out. Okay, let's move on to plan B, because that's not going to happen anytime soon. Good diet, more nutrients, less fatty, salty diet can help reduce your blood pressure. Exercise causes the release of some neurotransmitters that help to reduce these impacts. Sleep, this one's a big one for me because the more stressed out I get, the less I sleep, right? Which makes me more stressed out, and I'm sitting there laying there thinking, you know what would solve everything? Sleep at 4:30 in the morning as I'm looking at the clock. I'm thinking, you know, if I could only sleep. So, but there are other mechanisms. So let's move on to the other ones. And this is actually relatively new research too. This, again, has been done. There was a big research project in the UK, a bunch of government workers. There are some things that we know can actually reduce cortisol secretion and therefore reduce the effect. And some of these you've actually just happened into in your life. First off, doesn't surprise you probably at all that the more prepared you are for a stressful event, the less stressed you are going to get about the event. Yes? So preparation tends to reduce the cortisol secretion once you get into it. If you go into, for instance, a presentation and you're not prepared at all, your stress level is going to be through the roof. If you go into a test and you're not prepared at all, your cortisol level is going to be through the roof. So preparation, obviously, that makes sense. Other things that can help is to reduce the perception of stress. So this is like cognitive behavioral therapy. If there's anything that you can do that can recast the things that are going on in your life as, hey, this is temporary, it is not going to turn out as badly as I expect, then you can reduce cortisol secretion. Gaining control over your environment. This one's a little one, but all of us have experienced it. If I'm exceptionally organized about knowledge. My car is a total shithole. I'm not organized about everything, but about knowledge, like I have to have everything in the right place. I was the person who was neurotic and used the same pencil from freshman to senior year of college, right? I had to have all my crap. It has to be in the same place. I have to sit in the same place, right? Do any of you guys have this? How about trying to study when the house is a complete crap hole? Can you do that? No. You have to leave. You're like, I'm moving out, apparently. So you have to gain control over the things that you can gain control of because it actually reduces your cortisol. And remember, when you reduce your cortisol, it allows for your prefrontal cortex to work better. Now, the only thing that I need to caution you about is that trying to control other people, A, is doomed to failure, right? And B, increases their cortisol level, right? So you control your environment, not your humans, yes? They're just going to piss you off anyway. You can't control them, right? Okay, so that one's interesting. And then friendship and support reduce cortisol. If you have a supportive environment, the same situation will cause you to release less cortisol. And by the way, cortisol isn't very hard to test. You can just do a salivary cortisol secretion and you can test it. So they've actually done these. They did a huge study of government workers in the UK, and they looked at what they were doing, and they did some interventions and watched their cortisol level. I would love to do it to students, but they won't give me permission to test your cortisol levels. I would love to. I would love to like have an intervention and say, let's see if we can reduce their stress levels. And it's just like spit. I mean, you're not using it anyway, right? But they won't let me. They're like, it's a 2-year approval process. We need to go through the NIH. Oh, damn it. I just gave you guys a little. I can do it. Right? Friendship and support reduce cortisol. So what else helps is that there is another hormone, our friend oxytocin, which I wear right here. Oxytocin can help with this situation too. If you can do anything that will increase your oxytocin levels, what it tends to do is to counteract most of the negative effects of cortisol. Oxytocin actually causes vasodilation. What does that do to your blood pressure, guys? It lowers your blood pressure. And oxytocin, via a mechanism that we haven't actually figured out yet, Oxytocin is one of the few things that it can actually repair damaged cardiac muscle. So if your cardiac muscle got damaged but didn't die, right? A lot of times the repair of cardiac muscle is really, really difficult, but oxytocin increases cardiac muscle damage. So, and it also decreases the inflammatory response. So if you had inflammation associated, it decreases that response, and it increases trust between people. So since this helps when you're stressed out, how do you get more oxytocin? Well, you know some of them, but you might not know all of them. Welcome physical contact. It has to be welcome, or else it's going to cause you to release cortisol, right? So one of the many things about consent that we need to understand, both people have to be welcome consenting parties, otherwise bad chemicals are released. Play with your kids, right? Touch your kids if they want you to. Mine's 12 now, and he used to be my source of oxytocin. I just like snuggle up on and pull him out of my lap. Now he's taller than me, and he's like, get away. So now I guess I have to go to my husband, who's even harder to catch. He's like got shit going on all the damn time. Or my dog. Pets, actually, interestingly, this was a study that was just done 3 years ago. It was published last year, I think. Your dogs actually make you release oxytocin, and they release it too. Isn't that fascinating? A little co-evolution. They've been evolving with humans for so long that when you have matched gazes with your dog, unless you're pissed off at him, unless you just crap on your floor, but when you match gazes with your dog, you both release oxytocin. When you pet him, you release even more oxytocin. So pets actually do. Now, nobody tested cats. I am not hopeful. That's all I'm saying. Okay. Pretty sure that they would eat you when you were dead, but you can pretend. Maybe you release oxytocin and they're just like, whatever. So your pets actually do that. And sex will do it. Sex makes you have a big release of oxytocin, lowers your blood pressure, repairs a bunch of stuff. Friendship and human connections actually do it as well. Interestingly, you don't even have to be in the same room with a person if you're very, very fond of them. Talking to someone that you're very fond of on the phone can help you release oxytocin and calm you down. Not as much as if they're there in the room, and not as much as if you actually make physical contact. But nobody actually tested texting. I'm kind of sure it doesn't work, but I don't know. They didn't test the oxytocin level. So friendship, human connections, all of those things can help to reverse the negative damage of cortisol. Okay, anybody questions? Do you have plans for today that include cuddling, petting the dog? My little boy, by the way, this was long before this research came out. He's 12 now. When he was like 4 and 5, probably other parents have experienced this. He had night terrors. Anybody have kids with night terrors? They just go through this period in which they just like scream their head off in the middle of the night. It's more than a bad dream because they're not really very verbal and can't communicate about it. And it's terrifying for the parents, and you can't calm them down. And we tried everything. We like snuggled with them and warm baths before. But what we finally figured out after he had been having this for like 6 or 8 months, almost every night at almost exactly the same time, was the one thing that worked for that kid was the golden retriever getting up on his bed. He was still hardly communicating about what was going on. He would stick his hands into her fur, and then all of a sudden he would, and then fall right back to sleep. Worked every damn time. So now whenever he's stressed out, I'm like, okay, you just go get in bed. I'll bring you some hot chocolate and your dog. And then he's in bed with his dog, and he's like, okay, everything's fine. Everything's fine. So I also just wanted to show you guys an article. I will post this for you. Read it or don't read it, but it is kind of interesting based on what we've been doing. So this was just published recently in the journal Psychoneuroendocrinology, and there is a journal. Okay, and guess what it says? They just found out recently, this was just a couple weeks ago, or a couple months ago, August 16th. It is testosterone and cortisol and their ratios interacting that seems to predict how likely a dad is to care adequately for his children. And so there are certain ratios of testosterone and cortisol, and I find that pretty damn interesting. I'll post this for you and you can read it, right? You can go test. Maybe you're going to test the man before you have children with them, right? We test this, but then that makes them secrete cortisol, so I don't even know. Okay, all right, so now what we are going to do is move on to muscles, which you guys did in lab last week, okay? And with muscle physiology, so we're going to go through some of the stuff that you did in anatomy, and then we are going to go further than that. So, hold on. All right, so if you are one of those people that's really uncomfortable with the terminology and anatomy of muscle tissue, remember all the sarcos, right? You're going to need to go back and review that. You're going to need to go back and review the sarcoplasmic reticulum, sarcomere, sarcolemma, all of that crap. Because I'm going to assume that you know it, and I'm going to start with Roman numeral 2. We'll go through it quickly, but not slowly. If you really aren't confident with it, it's in interactive physiology. One of the things I like about interactive physiology is that it has an anatomy review before the phys starts, and you can play with the anatomy. And in addition, of course, it's in your textbook. Okay, so let's start on Roman numeral 2 and just briefly talk about what skeletal muscle does for you. So we know the first part of it. Of course, skeletal muscle makes you wiggle, right? But it's not just about wiggling. It's also about postural stability. So skeletal muscle contraction is necessary for me to stand in front of you or for you to hold your neck up. It's also about support. In some places, skeletal muscle is like supporting. So this skeletal muscle is, of course, for movement, but it's also pushing my guts back against my body wall. This skeletal muscle right here is keeping your junk from falling out, right? The pubococcygeal muscles. If you have a whole bunch of big-headed babies, you can rip the hell out of that, and you can have uterine prolapse, which is just flopping around down there. Not something to look forward to. They should definitely teach that when they teach sex ed, huh? Uterine prolapse. Guarding openings, your sphincters, skeletal muscle sphincters. Heat production, skeletal muscle contraction and relaxation produces heat as a byproduct, which is why shivering works. Stabilizing your joints. So if you have a bad back, they don't say don't use your back, they say strengthen the muscles around your back and your abs. And then skeletal muscle also helps keep your fluids moving. Now, of course, blood moves primarily due to cardiac muscle contraction, but in order to get it back up, you need skeletal muscle contraction to push on the veins, and then the veins have valves in them, and it moves up. So if you are more active, you're going to have better blood flow, and not just because what your heart is doing. Okay, so what we're going to do first is just look at what skeletal muscle needs. So if you look at skeletal muscle, we will see that skeletal muscle is really, really vascular, yes, and very highly innervated. It's really vascular because it's a really energetically expensive tissue. So this figure right here is staining skeletal muscle so that you can see the capillaries that are snuggling every single fiber. So it's super duper vascular. So if you look, for instance, at a steak, which is a cross section of a cow muscle, yeah, what you are actually seeing is part of the reason this steak is red is because every single cell has little capillary snuggle around it. Does that make sense? Okay, so it's really, really vascular. It's also highly innervated. And the innervation is every single muscle fiber, and you guys remember that a muscle fiber and a muscle cell are the same thing? Yeah, you can use them interchangeably. Every single muscle fiber must have a direct communication from the nervous system in order to contract. If, for instance, you lose the nervous system communication to that cell's paralyzed unless it regenerates. Now, that's not the same as cardiac muscle. With cardiac muscle, I could tell one cell to do something and it could tell its buddies because cardiac muscle has what? No, they have, how do they communicate with each other? Yeah, gap junctions. Yeah, gap junctions. Okay, so skeletal muscle doesn't have that. So here are some skeletal muscle fibers. What I mean is this is a nerve coming in, okay? Do you see the nerve coming in? And then it splits and it goes to all of these fibers. What I'm saying to you is if this part gets damaged, that one's paralyzed, okay? This part gets damaged, that one's paralyzed. Damage it up here and you can have paralysis of the entire muscle. So with that in mind, can you see how nerve damage can lead to muscle weakness? Yeah, because you lose control of some of the fibers. Or it can lead to muscle paralysis. Yes, go ahead.
If it was cut down lower on the axon, could it grow back?
Yeah, it potentially. So innervation, there is the possibility for reinnervation because this is just an axon. The cell's still alive up there, but it takes a long time for that to occur. If you've ever had nerve damage, a lot of times they don't know how much you're going to recover for about 2 years, usually. Okay, so does that make sense to you? You have to tell every cell what to do with skeletal muscle. Okay, so now I want to go back and look at the histology of skeletal muscle tissue. You guys remember that skeletal muscle tissue is basically striated and multinucleated. You guys remember that, right? So what we have to do is we have to acknowledge the things that you learned in anatomy. Unfortunately, all of that cell information that you learned in 1610, some knucklehead decided to rename every damn thing inside a skeletal muscle fiber. So you don't get to call it cytoplasm anymore, it's sarcoplasm. You don't get to call it smooth endoplasmic reticulum, it's the sarcoplasmic reticulum. You don't even get to call it a cell membrane anymore, it's called the sarcolemma. Okay, so all of that stuff that you learned, now they changed the name. They did it to me too. I was not involved in the decision, so don't throw crap at me. Okay, so a skeletal muscle fiber is the same as a skeletal muscle cell, and it has a lot of similarities, but it doesn't look anything like those little fried egg cells that you looked at in 1610. So it looks really different. So let's first remind you, if you haven't heard before, tell you that the prefix sarco is really commonly used to refer to microscopic muscle tissue, and it means flesh, sarco, okay? So almost everything in it is renamed a lot of times with the prefix sarco. So let's start learning a little bit about a muscle fiber. So this is a whole muscle cell. This is a skeletal one. We will deal with this elephant in the room in just a second, but let's start with stuff that you've already learned. First off, this one will work because the nervous system is telling it what to do, right? That makes sense? Okay. Now, the cell membrane or plasma membrane, you no longer get to call it that. It is still a plasma membrane. It's still a phospholipid bilayer with proteins stuck in it, but its new name is sarcolemma. Okay. So the sarcolemma is the plasma membrane in a muscle cell. Sarcolemma. Okay, and the sarcolemma, in addition to having a special name, also has a special structure. So let me show you what it's like. So please note right here that we're going to blow this up. Do you see? Blow this up right here. Okay, so here is the sarcolemma. It's really curved right there, but that's okay. We'll define that in just a second. But notice what the sarcolemma does is it leads to these little tunnels that go deep within the muscle. Do you see that? That's called a T-tubule or a transverse tubule. What that T-tubule is it is a continuation of the sarcolemma that allows you to, instead of just having an action potential that goes along the surface, if you continue the cell membrane, you can take the action potential deep into the cell, okay? Because what we will see a little later is that you're going to have voltage-gated sodium channels all along the surface, but then down the T-tubules. So it allows you to take that electrical stimulus and work it deep into the cell. That will be what ultimately causes contraction, okay? So that's called a T-tubule or a transverse tubule, and they're all over the place. You are seeing the tops of them right here. It looks kind of like a pore on the skeletal muscle fiber. That's a T-tubule or a transverse tubule. Okay, all right, so now let's look inside, okay? Inside here. First off, of course, it's going to have cytoplasm, or intracellular fluid, but now we're going to call it sarcoplasm. And notice that there isn't a whole hell of a lot of room for sarcoplasm because there's so much stuff in there, but there are some important things that we need to remember. First off, do you guys remember that skeletal muscle fibers tend to be multinucleated? You're only seeing one nucleus there, but if you look here, you can see nuclei, right? And do you remember that the nuclei in skeletal muscles are usually peripheral, like pushed up against the side? And can you see why now? Because the middle's really busy, isn't it? So they get pushed up against the side, peripheral nuclei. Okay, now, as far as mitochondria, compared to other tissues, skeletal muscle fibers have boatloads of mitochondria. They're shown in pink here.
Now, I know that makes sense to you, but tell me why. Why boatloads of mitochondria? Lots of ATP. It's really energetically expensive tissue, super duper energetically expensive tissue. Okay, so what we are going to see is we're going to store 3 things that are related to that story. So you have boatloads of mitochondria, but you also have 2 things stored in there that are not shown in the picture but are physiologically important. Inside the sarcoplasm, you also have a protein called myoglobin. And myoglobin is similar to hemoglobin. And hemoglobin binds to and carries what around in the bloodstream? Oxygen, yeah? Myoglobin binds to and stores small quantities of oxygen inside a skeletal muscle. Okay? Now, it's like an oxygen piggy bank. Okay, so we're setting this up here. Do you guys see what we're doing? We've got a whole bunch of mitochondria. To make ATP, we have just stored oxygen on myoglobin, and then the next thing you will see is that we also, inside every skeletal muscle fiber, store glycogen. And glycogen is stored what? Glucose, yes, exactly, glycogen. And what this is of course the liver stores glycogen too, but the liver is the savings account for the entire body for glucose. This is a piggy bank for every cell. What can you get out more quickly, your piggy bank or your savings account? Yeah, you can get it as your piggy bank, right? You knock that damn thing open when you need to get into it. So every single skeletal muscle fiber stores a little bit of glycogen, a little bit of oxygen, right? And has boatloads of mitochondria. Why is this important to store it there? Well, because this is your emergency response tissue, isn't it? This is the tissue that keeps you from getting hit by a bus, yes? So even if you haven't eaten in the last 72 hours, you still are going to have enough to run your skeletal muscle fiber for a few seconds. Does that make sense? And by the way, after you finish working out, the very last thing you do is put everything back into the skeletal muscle fiber so that it's ready for the next time you might get hit by a bus. So we will see that during this set of notes. We'll see how that works. Okay, so myoglobin and glycogen are both stored. The other thing about myoglobin is that when oxygen is bound to myoglobin inside the cell, it makes the cell red. Just like oxygen binding to hemoglobin makes blood red. So now we've got 2 reasons that a cow muscle or your muscle is red, right? You've got all of the capillaries in there, right? And then in each cell, you've also got myoglobin. Does that make sense? Okay. All right, so. It's not in the myofibril, it's in the sarcoplasm, around the myofibril. Does that make sense? They didn't draw it on here because it's actually a protein that's dissolved. So it doesn't like make any structural change here, but it's in here, like all in between those. Okay, everybody good? Okay, so now let's address 2 other things. Please note that these guys right here, these big long Vienna sausage looking things, I'm going to come back to those in just a second. But before we get to those, note that each one of them is wrapped in this like purplish net thing. That is called the sarcoplasmic reticulum. And what it really is the smooth ER in skeletal muscle. But it's different. I mean, smooth ER doesn't usually wrap around internal structures. Does anybody remember, people hardly ever do, what the smooth ER does in most cells? Do you remember? For some reason, like that one doesn't stick. If I ask you protein, you go ribosome. But the smooth ER in most cells does lipid synthesis. Okay, but here it does lipid synthesis plus an extra function. And the extra function is that it also stores calcium, and it stores calcium right here, guys, right next to the T-tubule at what we call the lateral sacs of the sarcoplasmic reticulum. I'm going to store calcium ions, and that's going to be really important because calcium is actually going to be what will ultimately cause contractions. So it's got the normal function of SR plus, okay? We're not particularly concerned about the normal function because it's not directly related to contraction. Okay, so that's the sarcoplasmic reticulum, and now we get to the elephant in the room. What the hell are these long Vienna sausage looking things? These are big bundles of contractile proteins called myofibrils. And guys, what they do is they stretch all the way to the end of the cell and attach to the cytoskeleton, yes? And they are going to be the thing that pulls to make the muscle contract. Does that make sense? So what we're going to do is we're going to break down the myofibril so that we can see what's inside it and talk about the contraction mechanism. And then we're going to go further than you did in anatomy. We're going to talk about how the nervous system stimulates it, how ATP is used, all of that kind of stuff, right? Does that make sense? Okay, so we're going to take this and we're going to break it down and we're going to look at it, right? Do you see what I'm looking at? Hold on. Do you see this jagged line to this jagged line? Do you see that? Okay. That is going to be a structure that's called a sarcomere. And notice that it's going to repeat over and over and over again along the length of the myofibril, kind of like boxcars on a train. Does that make sense? So now what we're going to do is we're going to take one of those and we're going to blow it up and we're going to look at it. Here it is here. Jagged line to jagged line. That's a sarcomere. So we're going to draw a bad sarcomere on the board because even good ones, have you ever noticed that even if it's a good picture, drawing your own bad picture tends to make you learn it better, right? To me. I only draw bad pictures, so I'm sure it's useful for me. All right, so we're going to do it just like we did in anatomy, but then we're going to go further than that. So from here to here is the sarcomere, okay? And the edges of the sarcomere are called Z-lines. In your anatomy book, I think they call them Z-discs, but it's the same thing, okay? From one Z-line to another is called a sarcomere. And remember, the relationship of a sarcomere to a myofibril is like boxcars on a train. We're just going to concentrate on one for right now. And you're going to have two primary contractile proteins you're going to worry about. We'll add a little bit more detail to it next time. The contractile proteins, the thin one attaches to the Z-line and extends toward the center, but doesn't always touch its neighbor. These are called actin, thin myofilaments. So let me just make that make sense to you so it's not memorization. Actin is the name of the protein. It's thin because it's going to be thinner than the other one that we learned. And myo means what, guys? Muscle. And filament means long, skinny thing. Okay? So actin, thin myofilaments. Okay. And then, of course, you guys learned this in anatomy, although did any of you guys not do sarcomere structure in anatomy? Anybody? No? Okay. It's been a little while, though. Okay. Floating in the middle and not attached to the Z-lines are the myosin thick myofilaments. Okay, it's a different protein. Okay, so let's add a little detail. If you look at actin really closely, and it's the blue-purple one up there, we're not going to add in its friends yet, but we will see that actin has all of these little binding sites. They don't look like handles, but that's the metaphor I'm going to use for them. It's got these little binding sites all over it. And those binding sites are called actin active sites. And it's the site that myosin will bind to. And then myosin, if you look at it more closely, you will see that myosin has little projections sticking up off of it. Do you see them right here? All these little projections sticking up off of myosin? Yeah? Yeah, those are... These are called myosin heads. Okay, so to start out simply with what happens with the sarcomere is this, guys. Under certain circumstances, and the nervous system has to tell it to do this, what's going to happen is the myosin heads will reach up and grab the actin active sites, and they will pull or pivot, yeah? And when they do that, what happens to the distance between the Z-lines?
It shortens, exactly. Usually we don't talk about this in a whole lot of detail in anatomy, but here's not what happens. You don't actually reach up, myosin heads right, reach up, grab the actin active sites and pull in one fell swoop. What you actually do makes more sense if you look at all of these active sites. So what you're going to do is you're going to reach up and you're going to grab one, and then you're going to pivot, and then you're going to let go, grab the next one, pivot, let go. So what's happening is you're ratcheting it closer together. You're not pulling it in one fell swoop, right? Grab one active site, move it over, grab one active site. So you're going to go. Every time you do a it actually requires an ATP. So this is incredibly energetically expensive. Does that make sense? So you're ratcheting the thing close, right? And remember, let's extrapolate back up to whole muscle for just a second. If I shorten a whole sarcomere, I can shorten many of them and then shorten a whole myofibril, right? Shorten enough myofibrils, I can shorten a whole muscle fiber. Shorten enough muscle fibers, I can shorten a whole fascicle. You guys remember fascicles? Shorten enough fascicles, I can pull on the connective tissue, right? That will actually pull on a tendon and move a bone, yes? But it all starts down here at the submicroscopic level. It all starts down here with this contraction. Okay, so I'll show you guys an animation in just a second. So the components of a sarcomere. The sarcomere is made mostly of actin and myosin. Actin has two friends. We're going to add them in just a little bit later. And the arrangement of the proteins is repetitive. And because of that repetitive arrangement of the proteins, what you will end up with is a banding pattern. And you learned the banding pattern in anatomy, but let's just make sure that you remember how it works. The banding pattern basically says that if I use a protein staining technique, wherever I have more protein, it will stain darker. And wherever I have less protein, it'll stain lighter. That means that this area right here is going to be the darkest area, right? Yeah? And that's called the A band. At the edge of one A band to the edge of the next will be the I band. So you're going to have dark, light, dark, light. Please note that in the middle of the A band, there's an area that's dark but not quite as dark. And why is it not quite as dark? Well, because it's got this protein, but this one isn't overlapping it. Do you see that? This little area right in the middle of the A band? That's called the H zone. Good? Got it? Okay. So one of the ways that they figured out how this contraction occurred was that they stimulated skeletal muscle under a microscope. And I want you guys to predict. If I stimulate skeletal muscle under a microscope, when it's relaxed, it's going to be striped like skeletal muscle usually is. But when it's contracted, what do you predict about it? What's it going to look like when it's contracted? Yeah, pretty dark, right? Everything's going to get pulled into the A band. So let's look at what that looks like. Okay, so here is relaxed skeletal muscle, and you can see the H zone, and the I band is really big, right? And then contracted, almost everything gets pulled into the A band, right? So you guys tell me, just to reiterate, A, B, and H. Which of those are going to change length upon contraction? H, yes. And I. Sorry, I said A, B, and I. A, I, and H. I band and H zone are going to change length, right? Now, here's a logic question for you. Does actin actually change length? No. Does myosin change length? No. All they do is slide past one another, right? So it's called the sliding filament theory of muscle contraction. When I was in undergrad, I took physiology like 20 years ago. I was an undergrad. It was a freaking hard class. But we, in our lab, still experimented with animals. They don't really let undergrads do that anymore. But one of the ways that I remember learning this is that we took a frog and we pitched him or anesthetized him so he couldn't feel anything. And then what we did was we stretched his gastrocnemius muscle across a light microscope, and then we stimulated it with an electrode while we looked into the microscope. And what happened is his muscle went from being striped, yes, to being almost completely dark. And then I took the electrode off, and it went from back to being striped, almost completely dark, back to being striped, almost completely dark. So you can actually see the changing in the muscle when you're actually dealing with a living muscle. Now, I do feel bad about the frog in retrospect, but also I think I got a pretty solid physiological understanding of what I was seeing through the process. Okay, so the sarcomere structure, you've got Z line to Z line as a sarcomere. Actin attaches to the Z line, myosin does not. We've got all of the patterns. The only one that a lot of times you don't learn in anatomy is what is stabilizing these in the middle is a protein called the M line. It's not particularly physiologically important, and we didn't know about it for a long time. We actually thought that, the myosin is just floating there, which doesn't make a damn bit of sense. How the hell is it going to float there? Please note, here's the M line right here. Do you see it? It's just stabilizing the myosin in the middle. That's all it's doing. Okay. All right. So let us talk about how a sarcomere contracts, and we are going to look at one single myosin head attaching to one single actin active site, and we're going to do that over and over again. As it reaches up and grabs one, pivots, lays back down, grabs the next one, pivots, lays back down, and grabs the next one, right? Okay. When a myosin head is attached to an actin active site, it's called a cross bridge. Good? So what we are going to have to do is we are going to have to look at how a cross bridge cycles from one to the next one. Got it? This is called cross bridge cycling. You ready? So here's the figure in your textbook. We're going to go through it relatively slowly the first time. First time we're just going to look at what the head does, and the second time we're going to add in where the ATP is used. Okay? So it's a circle. You could start anywhere. I want to start right here where you form a cross bridge. The binding of the myosin to the actin, that's the first thing that happens. Okay? Binding or cross bridge formation. Good? The next thing that happens is the pivot, which is called the power stroke. It goes like this, guys. Right? Okay? And then I can't do another pivot until I release and reposition, then I can grab the next one, right? Because remember that really the myosin is staying stationary and it's pulling the actin into it, right? So it's got to pivot, release, grab the next one, pivot, release, grab the next one. The metaphor you can think about is remember when you were a kid and you went on the monkey bars, right? Only imagine that you are a massive myosin kid, and instead of you moving to the end of the monkey bars, you're pulling the end of the monkey bars to you, right? So that's what's happening on each side right here. You're going and pulling the end of the monkey bars to you. Okay, so what is going to happen is this is cross-bridge cycling, but now what we need to do is we need to add in where ATP is used. Because I told you that ATP was used every single time you do that process. But to me, it's actually kind of counterintuitive where ATP is used in the process. Because when you look at it at first, what I would think, maybe you wouldn't, would be that ATP was used for this part. Isn't that what you guys would think? But if I tell you the metaphor of this as a catapult, you will understand that that's not where ATP is used. Because where do you put in the energy with the catapult? You put it in when you cock it, yes? And then the energy is stored, and then you get this for free because you put in the energy, okay? So that's the metaphor that will work right here, is you actually put in the energy on the front end so that you get this for free on the back end. So watch, okay? We're going to go through it one more time, okay? So I'm going to do it once, and then I'm going to make you flop your arms around because you'll remember if I do, okay? All right, so binding of actin to myosin, yes? Okay, that's cross-bridge formation. Notice that when it is bound, it's got used ATP on it already. Used ATP is ADP plus an inorganic phosphate. You with me? Okay, so what I've just done is I have bound actin to myosin. It's like I've loaded the catapult, but I haven't released it. What releases the catapult? Phosphate falls off. As phosphate falls off, that's what I get.
okay? But now I'm in this position. ADP is still stuck there. ADP falls off at the end, right here, after the power stroke, okay? But I am stuck here unless I put in some energy. So how do I release and reposition, guys? Bind ATP, hydrolyze it. Bind it makes it release, yeah? But I'm not back into position. I have to hydrolyze the ATP or use the ATP to get back into position. Does that make sense? So at the end, as we come around to the end, what do we have? We have a positioned catapult that's already got used ATP on it, right? And then we do the whole damn thing over again. Does that make sense to you guys? Okay, get your arms out, get to flapping. You ready? Okay, so I'm gonna ask you questions as you go out, okay? Ready? Okay, so I wanna do cross bridge formation, yes? Does that cost me any ATP? No, it does not. Now I would like to do the power stroke. What has to happen before I do it? No, phosphate falls off. Phosphate falls off, right? Now what has to fall off? ADP falls off. I'm stuck here unless I have what? ATP binds, that causes the release, but I haven't repositioned yet. What do I have to do to get repositioned? Hydrolyze the ATP to ADP and phosphate, right? Does that make sense? And you do this over and over and over and over again. And every single time you do, it costs you an ATP. So let's just extrapolate to what the hell that means. So if you look at this, first off, let's acknowledge that it's 3D, not 2D. So you are not just doing it along a two-dimensional sarcomere, but along a three-dimensional sarcomere, right? So it's thicker than you expect. And then how many sarcomeres do you have per myofibril? A bunch. How many myofibrils do you have per muscle cell? A bunch. How many muscle cells do you have per muscle? A bunch. Up to 100,000, depending on the size of the muscle. And that is what it takes to cause a muscle to contract. Now, can you understand why you can just sit around? If you put some work in on the front end to build a bunch of muscle mass, I'm going to pick on Scott, because I think Scott might have worked out once or twice. Why does Scott sit around, just sit around, and burn like a cheeseburger and a half? Why don't you just, well, because all that muscle tissue is really expensive to maintain, right? Muscle contraction is really expensive to maintain, especially when you understand that once you make muscle tissue, she works out all the time too. She's just got a little person in it. So muscle is really expensive to maintain, especially if you understand that once you have muscle mass, it is never completely relaxed. It always has tone, right? So muscle, even relaxed muscle has tone, especially if you've been working on it. So you can experience that if you sleep with a really hot person. I definitely do that at least once in your life. If you poke them when they're asleep, they're still hot. They are. Like they still got good muscle tone when they're hot. So, what?
They usually all men are warmer than women.
Oh yeah, men. Yeah, they usually do tend to have higher metabolism. They got more muscle mass. Yeah, muscle contraction is really energetically expensive. So we're going to get into this in more detail, but I just want to tell you before we move over on a topic, is that this also will help you understand how you can increase the tensile or contraction strength of a muscle. So if we just look at this one cell, okay, this muscle would be stronger if it had more contractile proteins, right? This muscle cell would be stronger. Does that make sense to you? Okay, so based on your experience with being a human, you know that how you build muscle strength, yes, is to do a combination of things. You lift something that is almost the limit of your capacity a couple of times, a few times. Can't do 25 if you're lifting a heavy enough weight. Does that make sense? Okay. So you lift something. That is communicating. What you are doing is communicating to your muscle cells. If you will also feed it protein and things that it will need for anabolic reactions and rest it so that it can spend its energy on protein synthesis instead of more muscle contraction, what this muscle will do is make more actin, more myosin, and more myofibrils, and it will get thicker and stronger, and then your muscles will get bigger. Does that make sense? So what doesn't happen to any appreciable amount in an adult person is you don't get any more muscle cells to speak of, but you can make each individual muscle cell stronger and give it more tensile strength. Does that make sense? Because more sarcomeres, more actin, more myosin, greater degree of contraction. Is that okay? Go ahead.
So what happens with muscle failure?
With muscle failure,
Yeah.
wait until we get to whole muscle activity and then we'll come back to that one. Okay, go ahead.
Okay, I know I've been over this like 3 times, but for some reason I'm still having a hard time figuring out when the ATP is used.
Okay,
in that.
so let's do it one more time. Everybody ready to flop? We're gonna flop for Anna. Okay, ready? Okay, so I wanna know when the ATP is used. Okay, you ready? So you have to do it if I'm gonna do this for you. Get out there. Okay, so I wanna do cross bridge formation. Any ATP used there? No. Okay, now I want a power stroke. What has to happen? Phosphate has to fall off. That was there from the last time the ATP was used, right? Okay, phosphate fell off. Phosphate fell off. And now what falls off at the end of the power stroke? ADP. Okay, got it? So ADP fell off. I'm still here. The thing that makes me release the cross bridge is ATP binding. So ATP binds and the cross bridge is released. But we actually haven't hydrolyzed or used ATP yet. Where we have to use it is to get that damn catapult back into position, right? Isn't that where you put in the energy with a catapult? You push it back down. Does that make sense? That's using the ATP. So what position is ATP in now? Is it still ATP or is it ADP plus phosphate? Because I just used it, right?
Okay.
So the release is binding of ATP. The repositioning is the hydrolysis of ATP.
Okay.
Does that make sense?
Yeah, just a lot of it's just like ADP, inorganic phosphate falling off.
Yes, inorganic phosphate falling off, ADP
Okay.
falling off, ATP binding, ATP
You don't think it's
hydrolyzing.
sticking around, you kind of just think of it.
No, it's sticking around. It's like, yeah. Mm-hmm. So, and you can also kind of understand why those mitochondria better be pretty close to the sarcomeres, right? Because what do these little guys have to do? They have to like pump out a whole bunch of ATP and get it right to the sarcomeres really quickly, right? Otherwise, you're not going to be able to do that. Okay. So let me show you an animation too, for those of you who are the visual folks. This one doesn't go through all of it. It only, actually, maybe it's this one. Okay, hold on. Wait, right there. What is this one called? Physiology notes. Yeah, go ahead.
With just randomly moving, like if I was going to pick up my pen like that, is that involving motor unit recruitment, or is motor unit recruitment just like if I need to pick up something that's heavy, and then I'm going to use motor unit recruitment to
So
more?
with recruitment, you always have some degree of recruitment is like how much muscle strength you need. But with recruitment, and we're going to do recruitment next time too, but with recruitment, if I pick up a pen, generally speaking, even a minimum level of muscle contraction would be adequate to do that. But if the pen was made of solid gold and I didn't realize, what's going to happen is I would have under-predicted the amount of recruitment that was necessary, and I would increase recruitment until I overcame the load. Does that make sense? So you always start with some low-level prediction of how many muscle fibers would be necessary. If it's inadequate, then you will continue to recruit until you either run into your capacity, right? Or you overcome the load. So if I do this, right, and I say, okay, I want to lift up this damn table, and I can't lift up the table, right? So what's happening right here and in my forearms is I'm recruiting until I have to accept the fact that this load is beyond my capacity to overcome. That make sense? But if I were a different person, I might actually be able to overcome it, pull it out, right? So recruitment always occurs, but you don't always need to go up from the recruitment that you predicted. Good? Okay, so let me show you this figure real quick. Hold on. Just wait right there.
It's really funny when people think things are really heavy and you're like,
I love it. That's when you over recruit. Like if you like look at it and it's a terracotta planter, but it's not terracotta, it's made of foam, right? Woo! Or at Chili's, they have glass mugs for beer and they have plastic mugs for everything else, and the glass mug weighs like a pound. And if you're not paying attention because you've been drinking too much beer, what happens is that you grab your water and you dump it in your lap, and they're like, no, I'm totally sober. Okay, hold on. I want to show you an animation real quick, but I can't. Not here. No, it's not that one. Oh, I'll just use this one. I'll show you the other one for just a second. Just to give you a visual of the stuff that we were talking about. So here's your myosin head drawn in a different color. Here's your actin active sites. And what is going to happen
This uncovers the myosin binding sites on the actin, allowing myosin heads to bind and form cross bridges.
Cross bridge formation, power stroke. Right. And it's going to be stuck there unless we have what around? Unless you have ATP around. That will eventually get us to understanding rigor mortis, by the way. Part of the reason you get stuck in that contracted position after death is because you're out of ATP. That's one of the problems with being dead. They're out of ATP. I mean, who knows? It might be really fun. We've literally never tried it and have no reports back. So, okay. So, basically what you are getting is the length of the sarcomere is going to shorten, but the length of the myofilaments doesn't change at all. And the H zone and the I zone may completely disappear with maximal contraction. Like you can get it actually contracted so much that you can make the actin like overlap so that there's no H zone at all. And the I band almost completely disappears too. Does that make sense to you guys? Okay. The length of the A band doesn't change much. I'm not saying that you won't notice it slightly getting squished if the sarcomere is maximally contracted, but it really is just staying in position. Okay. So to go back up to whole muscle contraction, and then next time we're going to add in the nervous system portion of it. So if you contract enough sarcomeres, you can contract in a whole myofibril. If you contract enough myofibrils, you can contract a whole muscle fiber. Enough muscle cells, you can contract a whole fascicle. Enough fascicles, you can generate enough tension to overcome the load of a bone, for instance, right? Does that make sense? Okay, now, for those of you who have been using interactive physiology, it's fantastic for both endocrine system and muscle. It's really, really good for endocrine system and muscle, so I would highly recommend that you guys use it. Remember, we're going to have a muscle lecture on Tuesday when you guys get back. I'm also going to upload a worksheet for you guys for muscle, and then we're going to do it in class, okay? So we're going to work through that worksheet in class, and then we're going to finish muscle. If we don't finish muscle on Tuesday, here's what's going to happen. I will post a catch-up lecture, and then when you guys get back from fall break, we will have your test, which will be endocrine and muscle. Yeah? Okay, so we'll get through all the hard stuff. We just might not get through some of the cool clinical applications, and I'll just post those. Okay? You all right?